Hi everyone, welcome back. In this video, we're going to be diving into something new I haven't done a video on yet. This is on radioactive decay and half-life. So earlier, we talked about in class, or perhaps you watched the earlier videos, on what happens when unstable nuclei decay, when they break down, right? But now, in this video, I want to look at not what happens, but more like how fast it happens, or like what happens to the number of nuclei over time. And we're looking at really this kind of exponential decay curve in here. But perhaps before we jump into half-life and the mathematics and the physics of radioactive decay, let's just go back and review a little bit about what is radioactive decay. Back in 1896, the French physicist Henri Becquerel discovered radioactive, by accident actually, storing some minerals in a desk, I believe, with some photographic plates. And so we now know that we have roughly 4.5 times 270 stable nuclei that are what we call unstable. They don't last for very long. They break down and they turn into something else, right? And so earlier we were talking about the types of decay that we have, all right? So we discussed alpha decay, we discussed beta decay, beta minus, beta positive decay, and we also looked at gamma decay. So maybe just a quick little review of that. Alpha decay occurs when a nucleus spontaneously disintegrates and turns into a daughter nuclei and emits an alpha particle. So you'll notice that the daughter nuclei has 2 less protons and 2 less neutrons, and that's why we have an emitted alpha particle. And you should know, hopefully by now, that an alpha particle is just really a helium nuclei. Then we have beta minus decay we discussed in class. Beta minus decay, kind of something interesting happens here. We have 1 more proton in that nucleus of the daughter, but 1 less neutron. So essentially a neutron gets converted into a proton. In order for this to occur, it emits an electron, or a beta minus particle. And we also have beta positive decay, or beta plus decay. And in this case, the parent decays into the daughter, and now we have 1 less proton and 1 more neutron. So basically, our proton gets converted into a neutron, and it emits what we know as a beta positive particle, or a anti-electron, or actually probably more commonly known as a positron. So it's basically a positively charged electron. And lastly, we discussed gamma decay, and in this case, we have some parent nucleus that has gone into an excited state. So essentially, an electron has been stimulated to a higher energy level, and then it has fallen back down. And when it falls back down to the lower ground state level, it'll emit a photon, basically a gamma ray. Okay, so that's what happens, right? What we're really actually looking at in this video is not really what happens, but how does it happen over time, right? How fast this decay happens. And I guess the forefront of this is that it's a random process. So perhaps what I'll do is I'll bring up an animation for a moment. So I found this animation online. I think it's pretty cool. It's a simulation that starts with essentially a large number of nuclei, 400 nuclei. And these nuclei are represented down below as these red spheres. They are essentially undecayed nuclei. They're the parent nuclei. And then they will gradually turn blue, if I press play here, over time. And that's the blue nuclei are essentially the daughter nuclei. All right. So you may notice this red bit of area is a little bit different, deviates a little bit from this purplish curve. So I should kind of talk about that. That purplish curve right here is a nice smooth function, and that's actually the ideal case. So if you go back to our notes here, you'll see here is this curve right in here, and there's a nice mathematical function given right there, right in there. That's the number of nuclei, and it can be described mathematically as n naught, that's the starting number of nuclei. Maybe I'll scroll up here, that's n naught is the starting number of nuclei, times E, which is Euler's constant, raised to the power of negative lambda times t. And lambda is known as the decay constant. So up here, the decay constant is a unique value that varies for each type of radioactive isotope. So it is going to describe how quickly or not so quickly this decay will occur. So perhaps we'll go back to the animation for a moment and try to explain it. So this is a medium setting, but if I go to like a small setting for half-life and I press play here, you can see the decay happens much more rapidly. If I change it to, say, a large one, then we will see that this is not decaying as quickly. So you can imagine that every nuclei has a different decay constant or half-life actually. So maybe we should discuss actually what is half-life. You notice there's small, medium, large. So if I go to medium here, you can imagine I start off with 400 nuclei and I get to some point where I'm going to, if I step forward, I might get, somewhere between that previous time, 14 seconds and 15 seconds, it was about 200 nuclei. At some point it was about 50% of the original nuclei. And at that time, in here, that would represent what we call the half-life, right? So let me explain it graphically in our notes here. So this is the starting number of nuclei. And so when this is half of it, for example, in our example, this was 400 nuclei. And so then when we get half of that amount left, now it's 200 nuclei. And then if we interpolate, this is known as the half-life. That's the time that it takes for us to have only 200 left. Now if we've gone through, say, 2 half-lives, 2 times this, then we're left with 1/4 of that. So that'd be like 100 or 25%. And you can keep going through here until eventually, after, say 9 or 10 half-lives, you'll only have like 1% left, right? So maybe a little bit about the mathematics. Well, we've already gone over this equation. It's on your formula sheet. And the other one that is on the equation sheet, but I forgot to put a box around it, is this one, right? And the half-life, or maybe it's like written this way on the formula sheet. The half-life is given as ln 2, which is just the number 0.693, divided by lambda, or vice versa. The decay constant is 0.693 divided by the half-life. Okay, so if I give you the half-life, you can find the decay constant, which belongs in this exponential function here. Now, you might be wondering, what are the half-lives? Well, every radioactive isotope has its own half-life, which you can look up in data tables. Here's a picture of one that I've just picked off the internet that shows you some selected radioisotopes and their half-lives. And you can see that the half-lives can be written in days or years or nanoseconds. And then they also show on the side what kind of decay mode they're going through, whether it's beta minus decay, beta positive decay, alpha decay, and then what kind of nuclei is produced with this type of decay. Okay, so on an exam, we either give you something graphically and we ask you to find out things from the graph, or we'll give you the values of the half-life or the decay constant and you have to calculate things or draw the curve out. So the best way probably to understand this, I would say, is to do an example. So let's move on to the next example, or the additional example in the notes. Okay, looks like I gotta remove this image. There you go. So in the graph shown to the right here, we have a graph showing the number of nuclei on the y-axis and the time that it takes. So we're asked to determine the half-life in terms of T0. So T half is, well, let's look at it graphically here, right? If we start off with this amount of nuclei, when does the half-life occur? So recall, that occurs when we have 50% or half of N0 of original nuclei that we have. And then we're going to have to use interpolation. So we go over to our graph and look at this and say, okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's really 5 units up. 1, 2, 3, 4, 5. That's N0 over 2. And then I'm going to interpolate this until it hits that curve, go down here, and then read that value. And that is 1, 2, 3, 4, 5, 6. That's 1/6 of T0. So essentially our half-life is 1/6 of T0. Okay, it's a pretty relatively straightforward example, hopefully. All right, let's take a look at another example. All right, example 2. So example 2 also has a nice graph shown here. And we are asked to determine a number of things. So now maybe before you just kind of listen to the video, I would say pause the video and actually solve it on your own. And then check what you get. I'm assuming you have done that. Okay, so let's go on. Part A is asking for how many atoms were initially excited. So if you look at this picture, this is actually showing you number of excited atoms over time. So you can see that initially we have essentially 200. So n naught is 200. It's the starting value. This is n naught, right? Second part. At what time have half the excited atoms decayed? So essentially what we're asking here is, what is the half-life? So T half is when we have half of the starting nuclei. So that would occur at, n naught divided by 2, which is essentially 100. So we move along here until we hit the curve. We're interpolating, and then we read the value, and that is 10 nanoseconds. So 10 nanoseconds is our half-life. Okay, part C. How many photons are emitted in the first 20 nanoseconds? All right, so 20 seconds is over here, right? And when we look across here, that means there are only 50 left of the nuclei that we started off with. So you can think of it as like you have a parent that is in some excited state that decays into a daughter that's not excited. I should put a little star there. She's not excited. It's just D. All right. And then you have a gamma particle, right? And this is just one sort of decay that has occurred. So if we're looking at how many photons were emitted in 20 nanoseconds, we're asking for, instead of asking how many undecayed we want to know how many have decayed. So we started with 200, we're left with 50. So how many have it decayed? So essentially, it's just 200 that we started off with, and we're now with only 50. So we must have had 150 photons that have decayed in those first 20 nanoseconds, if we're only left with 50. D, the decay constant. Remember, that's the symbol lambda. So if you recall, that equation is given to you on your formula sheet. That's lambda equals ln 2 all over T half. So ln 2 all over T half. Right? So that's like about 0.693 divided by 10 nanoseconds. All right? And that's going to give you roughly, if you pull that here in your calculator, 0.0693. And that's nanoseconds on the denominator, so it's nanoseconds to the power -1. Okay, of course, I'm rounding. You could add more values on this. I'm only going to 3 sig figs. And last part is to write this as a function of time. N as a function of time. Now again, that equation is also on your equation sheet. That's right over here, right? N equals n naught times e to the power of -lambda t. So let's write that equation out. N equals n naught e to the power of -lambda t. And then we're just substituting values that we have. We know that we started off with 200 nuclei. And it's e to the power of -lambda, which is 0.0693 times t. Okay. All right. I know it's a long video, but I'd advise to get all these additional examples done out of the way. So let's go on to example number 3. So example 3, we have a half-life for a particular isotope is 6.5 hours, and there are initially 48 to the power of 19 atoms in this isotope. So maybe, again, pause the video, try to do it on your own, and then check afterwards to see if you got the right answers. Okay, so we are given, in here, already just done given, we are told that the T half is 6.5 hours. And we're told the starting number of nuclei is 48 to the power of 19 atoms. All right, so we're going to go right straight to our solution here, part A. We are looking for the decay constant. If you recall, that's ln 2 all over the half-life. So that's 0.693 roughly, divided by 6.5 hours. That gives you an answer of 0.107 hours to the power of -1. B part. All right, So how many isotope will be remaining undecayed after 50 hours? So what I would do is write out the function for n. N equals n naught e to the power of negative lambda t. And then substitute values in here. We have 48 to the power of 19, right? E to the power of negative lambda 0.107 times t. So now what we're going to do is, you can think of this as n as a function of time. So n, or maybe at t equals 50 hours, we're just going to substitute the values in here. So 48 to the power of 19 e to the power of negative 0.107 times 50. And then we just simply put that into our calculator. And I get an answer of 2.32 times 10 to the power of 18 atoms. Okay, next, part C. Calculate the time for only 0.1% of the initial isotope to remain. So what we're looking for is essentially n divided by n naught, right? We want only 10%, not even 10%, sorry, 0.1%. That's like 0.1 all over 100, right? That's 0.001, right? So we know that's going to be true, right? So if we rearrange this equation here, we know that n divided by n naught is e to the power of negative lambda t equals 0.001. Right? So now let's plug in some values. Negative lambda, which is 0.107 t, equals 0.001. Now we need to get rid of the exponential function, so we're going to do ln. So we're going to do ln of negative 0.107 t. Well, actually, ln of the exponential gives you just, let me rewrite that, sorry for that in a while right here. That's actually, when you take the ln of both sides, you'll get negative 0.107 t equals ln of 0.001. So then t, all right, is going to be equal to ln 0.001 all over negative 0.107. And this gives you an answer of 64.7 to 64.8 hours. Okay, any more examples? Determine the fraction of isotope that is remaining after 1.6 half-lives. Alright, so we want to know essentially in D part what is n over n naught equal to when t equals 1.6 half-lives. And we figured out the half-life. Yes, it's 6.5 hours. So essentially we know that t is 1.6 times 6.5 hours, which is 10.4 hours. And then we're just plugging that into this equation, e to the power of negative lambda t. So e to the power of negative 0.107, yeah, times 10.4. And go ahead and put that in your calculator. And I get 0.3298, I'll just say 0.33, or 33% left. Okay, rather long video, sorry about that, but hopefully you're getting the idea of half-life and radioactivity, decay, and how it occurs over time. Just remember that exponential decay problems can be approached with either using the exponential formula or using the half-life fractions, or whatever the situation calls for. All right, good luck with the homework.